Okay, so for this example, we're going to be going in, and I took a sample of 14 males and a separate random sample of 15 females from Cosby High School. I asked them how much they spent on prom weekend, dress, meals, makeup, flowers, etc., all those things. And the amount responded to is recorded below. So we can see we've got a separate random sample of boys, and we've got a separate random sample of girls. So that's the first part that we need to take a look. So we got all our boys here, right? And we got all of our girls down below. Now, what might you notice? How many samples have we taken? And we've taken now 2 independent random samples. And what we want to try to figure out, is there statistically significant evidence that the true mean amount of money spent by all Cosby boys is different than the true mean amount spent by all Cosby girls? So let's just see how this is a little different. Before, we were able to do a 1 sample t-test, which we had 1 sample mean, 1 hypothesized value, and S over the square root of n. This was our formula for a 1 sample t-test. But now, if you take a look, we have 2 means. We have x bar of the boys and x bar of the girls. So we have 2 means, and this leads us to our 2 sample t-test. So we can see our 2 formulas that we have right here. Here's our 2 sample t-test formula, and if you take a look, notice what it says. It says x bar 1 minus x bar 2. So that's our statistic. Minus mu 1 minus mu 2, that's our parameter. That's going to be what we hypothesize. We'll talk about that in a second. And then s1 squared over n1 plus s2 squared over n2. This is the standard deviation of the statistic. Or we could think about that as our standard error. Now, how do you notice that this is different? Look, it's square root of s1 squared over n1. So if you actually notice, relative to what this was, that's our variance, right? We square both the top and bottom, and we end up with this. This is the variance. So what are we actually doing? We're just adding variances. So even though we're subtracting, remember variances always add because there's more variability. So we can see that. And same deal holds here with our 2 sample t confidence interval. Alright, so let's go ahead and walk through this. So this is asking us, is there statistically significant evidence? So that's asking us for a phantom. So we'll start off with our parameters. Now we've got 2 means this time. We got mu b and mu g. Alright, and I'm going to type this out to make everybody's life easier. So what is mu b? Mu b is the true mean amount all Cosby boys spent on prom. Okay? And what is mu g? It's the true mean amount all CHS girls spent on prom. And that's my population that I can infer to, so we got to be careful about that. I have a sample of Cosby students. This would not apply to all students in the United States. So we have 2 parameters that we need to define now. Alright, so let's go to our hypotheses. So for our hypotheses, it's going to be slightly different here, because obviously it's a little bit different, and we'll keep this under our fruit. So our hypotheses are going to go like this. We got our HO and we got our HA. So I'm going to start off by seeing what we want to prove. I want to prove that the mean amount spent by all boys is different than the mean amount spent by all girls. So that would be mu B does not equal mu G. So that's what I'm going to start off by assuming, trying to prove. So what do I begin by assuming? Remember, these should be the exact same mu B, but it's always going to be equal here, mu G. Now, we could write it also another way, and you don't typically show both of these, but if it helps you get it started, we can. If I subtract both of these over, mu B minus mu G would be equal to what value? 0. And then mu B minus mu G does not equal 0. So this actually is my hypothesized value, which is going to be dumped in right here. 0 is going to be the value. And 90% of the time, that's what we're going to be working off of, is the value of 0. Alright? So let's go ahead and figure out our conditions. So, our conditions are a little bit different here, and we're going to make life a little bit easier. What we need to have is we need this sample has to be independent from that sample. So those 2 samples must be independent. We also need independence within the samples, but we're not going to go there with all of that. So what we're basically going to do is we're going to type we have independent random samples. And actually I'm going to put 2 independent random samples. 2 independent random samples of boys and girls. And there we go. Okay, so we're just going to make our lives easy and we're just going to go with that. Alright, the third one is our normality / large sample condition. Now if you notice right here, I've given you the normal probability plots. So what do we notice about both normal probability plots? Do they follow the linear pattern? Yeah, so these samples look approximately normal, so we can infer that the populations are approximately normal. Also in the dot plot we see Remember, our large sample condition is if it's less than 30, we just need no outliers, and super strong skewness would be bad. And we see that we're both good with the dot plots as well. So what I'm going to check here is our normality / large sample. And I'm going to make mention both normal probability plots show a linear pattern. So we can assume both populations are approximately normal. All right, great. All right, so now let's go to name our test. So we got a new test, right? This is going to be our 2-sample t-test. Why? How many samples do I have? 2. It's pretty easy. Now we know that whenever we do a t-test, we need degrees of freedom. Now there's a couple of ways to get degrees of freedom in this. So the first way would be that we come up here, and the easiest way is to pick the smaller of the 2 sample sizes. So I have 14 versus 15, so the smaller is 14, and so I would just simply do 14 minus 1. Now remember, the t-distribution gets better as our degrees of freedom increases. So this actually is going to give me a more conservative p-value than if I used a different one. Now the calculator is also going to give us one that's more accurate. That uses this long formula that we're not going to do, but we can just steal from the calculator. That's totally fine. So I'll come back and actually fill that in. All right, let's go grab our t-test statistics. So here we go, ready? It's the t-distribution, so it's t equals. We take our statistics, x bar 1 minus x bar 2, minus the parameter mu1 minus mu2, and divide by the standard error of the statistic. So s1 squared over n1, we're just adding variances, plus s2 squared over n2. And you might say, this thing is a beast. And I agree. And what I would encourage you to do is on the AP test to not even show this formula unless you're really sure about it. Okay? So unless you know it, don't show it. You can really just get away with saying 2-sample t-test and writing your t-test statistic. I'll show you that here as we keep going. Okay, so x bar boy minus x bar girl. So 229 minus 302, that's our first part. And really, we're just trying to assess how far is this difference away from my hypothesized value. Now remember, what do we hypothesize? 0. We said that they should be the same, and we're going to prove that they're different. So there we go. So I may not know the exact values of mu1 and mu2, and that's okay. I'm just assuming that their difference is 0. Okay, divide by, and now we got to do s1 squared, so that would be 45 squared over 14 plus 89 squared over 15. All right, from here we're going to the calculator. We're not going to do this by hand. Too many spots to make mistakes. So in our calculator, first blank column, first blank row, menu, stat test, 2-sample t-test. There we go. And I've got the data. All right, so list 1, I've got everything in boy and girl. Just try to keep it in the same pattern that you've been doing it. And then our alternative hypothesis is not equal to. Okay, so then what we'll also notice is that asks us this question of pooled. We're always going to say no to that. If you keep going in stats, that talks about the population variances. So if the population variances are the same, then we'd say yes, but basically I would just always say no on this one. Okay? So hit OK, and there's our t-test statistic, there's our p-value, and there's actually the more accurate degrees of freedom. So we can see how that all works out. Let's go back in and fill this out, and we could see if we need the x bar 1, x bar 2, s1, s2, all that good stuff. So it gives us everything that we need. Okay, so my test statistic is negative 2.89, and my p-value is 0.009. So let's just again remember what this means. Here is my t-distribution, here is 0, here is negative 2.89, and this is part of my p-value. But since it's two-sided, I also have to go to 2.89. And this is all my p-value. Okay, so just remember that. Okay, so we're going to obtain our p-value, which is 0.009. Okay, and what do we want to choose for an alpha? So what would be acceptable for a type 1 error? And let's go 0.05. So alpha, let's go 0.05. All right, it's always a good one. So what do we know? We said rare is 0.05. 0.009 is less than that, so 0.009 is less than 0.05, so therefore we do reject HO. And when we do reject HO, that means we do have statistically significant evidence that what? That the true mean of boys and the true mean of girls is not equal to. So let's go ahead and see. So we have statistically significant evidence true mean amount all Cosby boys spent on prom is different than the true mean amount spent by all Cosby girls. Okay, but that's all that we've said. We've said that they're not equal to each other. So let's add a little more into this thing. Let's add a confidence interval. All right, so our formula for a confidence interval looks like this. Same formula from before. So x bar 1 minus x bar 2 plus or minus t star square root of s1 squared over n1 plus s2 squared over n2. Okay, and again, we could go back and fill this in, but I'm just going to go to my calculator and run this thing. So I'm just going to slide over 1 because we already did all the work. So menu stat confidence intervals are 2 sample t. Okay, we've got the data. Boy, girl. Alpha is 0.05, two-sided, so we use a confidence level of 0.95. And here we go. So it's negative 129 to negative 21. All right, so negative 129. Okay, so what does this tell us? This tells us that we are 95% confident the true difference in the mean amount on prom by all CHS boys minus all CHS girls lies in the interval negative $129 to negative $21. And we could also say that girls on average spend between negative $129 more and $21 more. Again, let's just remember, we rejected the HO. What did our HO say? That they were equal. What value do you notice is not in this interval? 0, so we could have also rejected from there. Alright, so there's our 2 sample t-test and 2 sample t-interval. Again, walking through, we took 2 independent random samples, and we're comparing their means, the 2 means of those two, mean 1 and mean 2.